B2. B2 is a particle in a box problem, and so this is the 2D particle in a box problem. There was somebody who requested the 1D particle in a box as one of the later choices. I'm probably not going to get to that just looking at time, right? We're already at the halfway point roughly. The same approach that we're going to be using for this right here, you would use for the 1D particle in a box. And even in this case right here, right, looking at the 2D particle in a box, you're basically just taking, the same approach that you would do for 1D particle in a box is, right? You're just doing it in two different directions and then combining them together. That's all you really need to do in these cases, right? And so if we're looking at, the equation for the 2D particle in a box, right, you can see that you can have essentially the particle in a box in the x direction, right? And that's the first part of it, right? Where it's the square root of 2 over lx times sine of nx pi over lxx, right? That's just simply the x direction, right? X direction, right? And then the other thing is the same thing, right? But now in the y direction, right? So you're just simply looking at a 2D coordinate system, essentially, in this case. And so when you go through and you try to determine the probability, and so one of the things too, right, is like I have videos showing how to go through these, both quantitatively, if you are, calculus minded, which we don't have to be for this class, or you can do qualitatively, which I'm going to do right now, where you can kind of figure out what's going on. And so the way to approach it, right, in my mind, is always simply just draw out what everything looks like, right? So we're going to take this right here. I'm just going to draw a simple box, right? This is the x direction. This is the y direction, right? This is L, 0, L, right? The distances are the exact same for this part right here, but you can still do the same thing roughly if they're not the same. Because it comes out basically being the same thing. So now, what we're looking at in this case right here, right, is it says in an LXY equals 0 to LX equals 3/2 region, right? So if we just divide this in half, right, this is L over 2 then right here. This is L over 2 right here. When n equals 2, right, we're trying to figure out what the probability of finding an electron is in those regions, right? Not a specific point, just simply in those boundary conditions. So the easiest approach, in my mind, is to first draw out what the wave functions look like at those different n levels, right? And so to do that, right, we know when n is equal to 2, right, you're going to have essentially a node at the halfway point in those cases, right? That's going to be the case for all 1D particle in a box type things, right? So in this case right here, right, you're going to have positive, and then it's going to go down here. It's going to dip. And then the same thing's going to happen right in this direction, right? Because they're both n equals 2 in these cases, right? So you have both of these right here. And so if I divide this up into quadrants, right? One thing I can see right here, right, is that if I were to just simply apply the 1D particle in a box approach, right, for the x direction, what I can see that if I'm stuck in this region right here, the probability of finding an electron is going to be 50%, right? Half of the time it's going to be on the left side of that box, right? Half of the time it's going to be on the right side. It's always going to be the case, right? It doesn't matter what is going on in those instances, right? It's always going to be something like that. And that's going to tell us, right, and that's the same as being 1/2, right? In those cases, right? The probability of finding is like, 1 over 2. Same thing over here, right? Is if we look at it qualitatively, right, 50% of the time, the electron is going to be hanging out in this part, in this region right here, right, which again is 1/2. So if it was a 1D particle in a box, right, and we were just looking at going from 0 to L equals, equals to L over 1/2, like the halfway point for n equals 2, right, in each one of those cases it would be 50%. But because we're looking at a 2D particle in a box, right, now we're looking at both of those percentages now essentially stacking up. So we have to multiply them by each other in those cases, right? And so if we have 1/2, right, times 1/2, right, that gives us 1/4, right? And so 25% of the time, right, a quarter of the time, right, 0.25, 25%, right? 25% of the time then, right, this region, which is what we're looking at, right, this is what we're trying to figure out. 25% of the time, that's where you're going to find the electron in a 2D particle in a box. If it was 1D particle in a box, right, it would be 50% of the time, but because we're looking at it in 2 dimensions now, right, that's going to cut it up a bit more. And And that's all the approach really is, right? You just simply do that right there. So the next thing, right, we can do another one. So if I draw it out, so this is the X, this is the Y, L, 0. So now we're going from the 0 to the 1 point, right, which is right here, right, or to L, and N is equal to 1, right? And so if we look at it, it looks like this, and then this one would then look like that right there. But again, because we're looking at this whole region, right, that's going to be 100% of the time you're going to find the electron in that region. And then in this case right here, right, again, it's going to be 100% of the time because it's the full region that you're looking at. So 100% times 100%, or like combined with 100%, is 100% of the time you're going to find the electron, right? Because you're looking at the entire box. We're not looking at any small regions or anything like that. Again, right, it's just simply, looking at, drawing it out, visualizing what's going on, and applying that. Now, the next one's going to be a bit more tricky, right? The third one. So if we draw this one out, we'll draw this one a bit bigger, right? So this is going to be the X direction. It's the Y direction, right? This is L. It's L, right? This is 0, and this is 0. Right? So we're looking at is the N equals 3 wave function. And so in the N equals 3 wave function, that means then at the L over 3, point, there's a node there in the 1D particle in a box. Right, this is L over 3 here, right? And then you also have one then at the 2L over 3, right? Because that's 66%, right? 2/3. Right, so you'll have nodes there. I know it's terribly drawn. Disregard the distances there, right? Same thing here, right? Because these are both going to be these, right? So this is L over 3, and then 2/3 L, right there, right? And so we can just draw them out, right? The wave function would look something like this. Same thing here, right? The wave function would look something like this, right? That's what the N equals 3 wave function looks like, right? For 1D particle in a box. It's just simply those. And so we can just apply those to the X direction and the Y direction. Now, the question is, going from the L equals half region, right? So this region right here, to the L over half, right? So that's the halfway point. So this point right here, right, for both of them, what is that percentage? So if I draw that here, and this is the half, right? What we're trying to figure out is what percentage of the time are we going to find the electron in that region right there, that shaded in region that I have in that box. So the way to approach it, right, is we can look at it and we can start breaking things down. So we know that this region right here, right, is always going to be 33% of the time, right? We know that this region right here is going to be 33% of the time. We know that this region right here, right, is going to be 33% of the time, right? 33.333, right? It's going to be a third, right? I'll just say a third. Right? A third of the time it's going to be in each one of those different quadrants. Now, what we're looking at is taking this quadrant right here and cutting that essentially in half, right? Because going from 1/3 to 2/3, right, 50%, right, the 1 over 2 region is going to be the halfway point. And so what we're doing now is we're actually going to then be taking, instead of that whole region right here, right, this right here that we're looking at is going to be 1/6 of what we're actually working with in that case, right? And the same thing over here, right? This is 1/6 of that region, right? Of the Y component. And so taking that right there, right? All we have to do, same thing, is just simply 1/6 times 1 over 6 is equal to 1 over 36, right? And you have that, and so you can convert that into a percentage, right? That comes out to being 0.0278, which is the same as 2.78%, right? And that's all you got to do in that case, right? It's only going to be showing up in that region that small amount of time, right? The probability of finding it in that specific space. And again, I didn't have to do any kind of calculus. I didn't have to do any kind of integration. I didn't have to do any of that stuff. I could just simply visualize my way to it and talk about it there. And so that's all you do for that part, right? You can just simply draw your way there and you just simply try to figure the things out. Now, if we start giving you guys like really weird regions that aren't clearly defined, that you can like identify by eye, then yeah, you're gonna be running into a bit of a problem. But that shouldn't be the case because you have to actually use calculus and integrate the different regions to get there. And that'll be a bit trickier. I do it in the video that I posted to YouTube, but again, you don't have to know how to do that for this class. The next part, right? Part B. So now what we're doing is we're going to be applying, we're going to calculate the energies, right? And so it's, again, pretty similar to what it was for a 1D particle in a box, where you have the equation, right? Where it's, h squared over 8ml squared times n squared, right? And n is the energy level, h is Planck's constant, L is the length of the box, m is the mass of the particle that's trapped inside of there, in those cases, right? And it's just plug and chug at that point, right? And so right, the 1D particle in a box equation, let me just write it out, is just simply h squared over n squared over 8ml squared, right? Where this is Planck's constant, right? This is the mass, length of box, and then this is the energy level that you're looking at in those cases. Now, one thing I want to point out, right, is that because of units, right, and this was, I think, in the earlier particle in a box problem, where I think I tried to make you guys prove that the energy ends up being in joules, which doesn't make sense just straight up looking at it, is that you have to make sure that the mass is in kilograms, right, and the length is in meters. Otherwise, things don't cancel out. That's just an important thing to figure out, right? And that has to do with the fact that a joule, technically, is, I can't remember off the top of my head, I think it's like kilogram squared times meter squared over second squared. Yeah, right? A joule is equal to kilogram squared times meter squared over second squared, right? And so, that's technically what a joule is actually those units. It's not the units that we're so used to. But that allows us, right, to cancel things out in those cases, right? Why the mass is important to include, why the length of the box has to be in meters, and so forth, right? Because all of those things help cancel things out and get you to having a final value of joules, right? Because h is joule seconds, and so things, right, end up canceling out. Cool. Alrighty. So yeah, so let me calculate these things, right? So all you have to do is just simply use the 2D equation, right? And so all the 2D equation is, in these instances, right, is for the 2D particle in a box, is pretty much the same equation, right? It's still h squared, still 8ml squared, right? It's still all those different things. And so this specific equation only really works when L is the same for the both different directions, this simplified one, but you can also do it the same way, right? Because you can just simply would have it be slightly different, right? I guess here I can just write it out so that way you guys can see it, right? So let me just block this off, right? So 2D, right, would be h squared over 8m, right? So those are all going to be constant through all of them. And then you would just simply have then, right, nx squared over lx squared plus ny squared over ly squared, right? And that would be the case, right, where the n levels are different for the x direction and the y direction, and the L levels are different for the x direction and the y direction, which can happen, right? They don't have to be exactly the same. They can be different. But what you can do, right, is if the L values are the same, right, you can just simply, simplify this and make it h squared over 8m L squared over nx squared plus ny squared. Now, an important thing to point out is you may be wondering to yourself, Eric, why didn't you simplify out the nx and the ny and just simply make those exactly the same as well, where you would just simply be like 2n squared? And that has to do with the fact that the nx and the ny, they don't have to have the exact same energy levels, right? They can be different in a 2D particle in a box. And so you're gonna, if you were to just do that shortcut, you're gonna miss out on a whole bunch of energy levels If you do this on an exam, you're going to get really bad grade. So that's an important thing to think about and pay attention to there, right? And so the way that you would do this, right, is you can just simply plug in the values that you have. And so we have the 1.5 value, right, for the distance, right? And so it's in angstroms. And so, L is equal to 1.5 angstroms. And so 1 angstrom is equal to 1 times 10 to the negative 10 meters. And so that comes out to being 1.5 times 10 to the negative 10 meters in this case. And so, we can just simply, do that conversion right there, right now. And then what we're looking at, right, is an electron in this case. And so the mass of an electron, I don't remember off the top of my head. I usually do by the end of this whole sequence of everything because I've used it so many times. But right now I don't, which is 9.11 times 10 to the negative 31 kilograms, right? So now I have L in the right units. I have M in the right units, right? H obviously is going to be in its own units, right? That's Planck's constant. And then N, right? The energy level, those are unitless. So the first thing to do, right, is now what we're going to do is we're going to look at, we can calculate now all the different energy levels. And so I'm just going to simply, right, if we look at it and we have, the N equals 1 and Y equals 1 energy level, all we would do in this case to calculate the energy is we would go through and we would use our equation that we have here, right? So h squared over 8ml squared times nx squared plus ny squared, right? You could do that right there. Now, one thing you can do, especially if you're ever given a problem like this where you have to calculate a bunch of them, is the only thing that's going to be changing, right, is this part right here. This part right here stays exactly the same no matter what the energy level is, right? Because that part's independent. So what I can do is I can just simply calculate what this part is all on its own beforehand, right? So h squared is 6.626 times 10 to the negative 34. Actually, let me do that calculation down here, right? So if we have h squared over 8 ml squared in this case right here, what that gives us is 6.626 times 10 to the negative 34 joule seconds, and this is going to be squared over 8 times the mass, which is 9.11 times 10 to the negative 31 kilograms, times L, which is 1.5 times 10 to the negative 10 meters squared. And so what I'm going to do real quick, actually, just for my own sanity, is convert that joules into the SI unit so that way I can make sure things cancel out properly. And then we end up with everything the way that we want it. So what we have is kilograms squared times meters squared over seconds squared times seconds, right? And so the seconds cancels there. And so that gets squared like that. And so then if that gets squared, let me just do the math part real quick. So what we have is 6.626 times 10 to the negative 34 squared. So that comes out to being, I'm just going to go in this direction. So that comes out to being, whatever, I'll just do it down here. 4.39 times 10 to the negative 67. Now that becomes kilograms to the power of 4 times meters to the power of 4 over seconds squared. And then that divides all that stuff down there. So you have 8 times 9.11 times 10 to the negative 31 times 1.5 times 10 to the negative 10 squared So that comes out to being 1.6398 times 10 to the negative 49. Can you guys all see that? Yeah. In that case, right? And so then the units are kilograms times meters squared. Something is missing. Did I forget to square something? Mm-hmm. In terms of units, oh wait, I'm off. Right? A joule isn't a kilogram squared, it's a kilogram. So this is kilogram squared there. Okay. We're good. I was worried there for a second because I was going to end up with kilograms to the power of 3, and I was like, that doesn't look right. Okay, right, so we have kilograms right down here. That cancels out, so that goes back to normally being kilograms. Then we have meter squared down here. That changes this to meter squared, right? So now we're back to being kilograms times meter squared over second squared, which is what a joule is equal to, right? And so that equals, and so then that means all of that. So then 4.39 times 10 to the negative 67 divided by 1.6398 times 10 to the negative 49 comes out to being 2.677 times 10 to the negative 18 joules, right? Because it'll be kilograms times meter squared over second squared. Right? And so that's what this whole thing right here is equal to. So all I have to do is just simply use that value in each one of these cases. And to me, right, that seems like a reasonable number, right? Because just thinking back to the Rydberg equation, right? The Rydberg constant is like 2.1, what was it? 2.18 joules times 10 to the negative 18, right? So it's in the same region, right? What that value right there is to what we have for the Rydberg equation. You know, the mass is the same, right, for both of them, right? They're both for electrons in those cases. And a distance of 1.5 angstroms, right? That's the distance of a bond. So that's not unreasonable, right? Distance for an electron to exist in. And so like that region of joules makes sense to me. If it was times 10 to the negative like 30 is what my answer was, I'd be kind of worried for something that's a pretty close, you know, physical model. You know, and that's, you know, an important thing to kind of develop in terms of intuition, just as a side note, right, is thinking about what everything can actually equal. And what, you know, what the ranges should be, you know, having like things that just seem like completely out of whack, for something that, you know, should make sense, right? If somebody, you know, tells you that, you know, all of your blood should be able to fit into like a 2-liter, you know, bottle, you should be able to think for a second, like, wait a second, I know what a 2-liter Coke bottle looks like. I shouldn't have, you know, only 2 liters of blood, or something like that, right? Like kind of relating it to other things that you're familiar with. That's kind of a morbid example. But anyways, so yeah, so what I can do here, right? So I can just go back to that equation that we have up here and just plug that value in, right? So we have 2.677 times 10 to the negative 18 joules, right? And so then now, since we're doing it for the n equals 1 and y equals 1 value, right, it's to simply be 1 squared plus 1 squared in that case. And so that comes out to being, right, equal to 2. And so the energy of the lowest energy, like the ground state for this system that we're looking at, is that value times 2, comes out to being 5.35 times 10 to the negative 18 joules, which is, I believe, what I have on the key. Yeah, 5.35 times 10 to the negative 18 joules, right? So you have that right there. Now, for the next energy level, right, there's two different combinations that you can have, right? So you can have the nx is equal to 2, and then ny is equal to 1, right? So you can have that combination, and we can go through and do that calculation, right? So in this case, that energy is going to be equal to, oh, come on, pen. See, this is what I'm saying. This is why the surface is garbage. Literally mid working on it, it just stops working. Right, so you have E is equal to 2.677 times 10 to the negative 18 joules. And then now you have 2 squared plus 1 squared. And so that comes out to being equal to 5, right? Because 2 squared is 4, 1 squared is 1. So you have that. And so then the energy for that energy level is 2.6771. I'm just going to store this as x because it'll make my life easier. So I can just simply do 5x in this case. And so that comes out to being 1.334. No, not 4, 9. Times 10 to the negative 17, right? And I have, I think, 1.34, yeah. Joules in that case, right? So that's what you get there. Now you can have the other combination, right? So you can have nx is equal to 1, and then ny is equal to 2 in that case. And so all that changes there, right, is that you have the same equation, but now instead of it being 2 squared plus 1 squared, it's just simply then 1 squared plus 2 squared, which still gives you 5. And those are going to be the exact same values, right? And so this is going to be degenerate, right? And the the definition of degeneracy in energy terms and all of this stuff is that you're at the exact same energy, right? So you have two systems that are technically different, right? So even though they look on paper exactly the same, and if I were to draw them out, they would just simply look like mirror images of each other. They're technically two different states. They're two different quantum states, right? Where you have n equals 2, ny is equal to 1, and nx is equal to 1, and ny is equal to 2. They're two different quantum states, but they come out at the exact same energy, and therefore they're degenerate and stuff, right? And so that's how you would approach it, right? And so you would work your way through, and so then, the next, after, doing this right here, the next one you would have, right, is the nx equals 2, and y is equal to 2. And then after that, right, what you can start thinking of is, the first thought that most people jump to is nx equals 3 and y is equal to 2. But that actually skips over a lower energy orbital, right? And that's going to be where nx is equal to 3 and ny is equal to 1 in those cases, right? And so, right, you can still have things that are like further apart, between those two different axes in those cases, right? And so, that's again an area where people kind of fall into pitfalls, is that they just, automatically are just going, each number is going that way, right? Not completely forgetting all the other combinations that you can do in those cases. So, but that's that, right? So that's part B. So that's how you approach calculating those energies. And so again, right, if you're just simply doing a 1D particle in a box, it's the exact same thing. You're just simply, plugging away numbers in those cases, right? Again, just making sure that the mass is in kilograms of whatever the particle is, right? And that the length is in meters in those cases, right? Otherwise, the units aren't going to cancel out, and you're going to end up with really weird numbers, and you're not going to technically actually have your thing in joules. So yes.